Hi, Ben. All right, you guys, I'm going to go ahead and start because it's 4:01. And I don't know if you saw my announcement, but I'm going to try to get through section 6.2 and 6.3 today. There are 4 objectives in 6.2. It covers one-to-one functions and inverse functions. And here's the first objective. Basically, a one-to-one function is literally exactly what it sounds like. For every one x coordinate, there is only one y coordinate that goes with it. It's one-to-one. So in these examples here, you can see that x sub 1 is paired up only with y sub 1. X sub 2 is paired up only with y sub 2. X sub 3 is only with y sub 3. Lines are perfect examples of one-to-one functions because it's a straight line, no curves in it. Every x has only one y, every y has only one x. The next 2 are not one-to-one functions. Because on this one, you have both x sub 1 and x sub 2 sharing y sub 1. That's not 1 to 1. That's 2 to 1. And then the last one isn't even a function because it violates the function rule where 1x goes to 2 different y's. So that's not even a function, but it's not 1 to 1 either. So that's all 1 to 1 means. Every single x has only one y coordinate associated and vice versa, period. So 2 examples, determine whether it's 1 to 1. I can see right here that both the 55 and the 61 share a 38. So part A is not 1 to 1 because there are 2 different inputs for the same output. And then the next one, part B, wants to know, is this 1 to 1? When I look at it, I've got a -2, a -1, a 0, a 1, and a 2. All of my x's are different. And then when I compare them to the y's, a 6, a 3, a 2, a 5, and an 8, all of the y's are different. So this is 1 to 1. It is 1 to 1 because there's no repeat anywhere on x's or y's. Nothing is sharing nothing. Okay, then I go on to talk about the horizontal line test. The vertical line test determines if it's a function. The horizontal line test determines if it's a 1 to 1. And if you can draw a horizontal line through this and it crosses in 2 places like this example does, you have just found 2 different inputs with the same output of H. And that violates the 1 to 1. So vertical determines whether it's a function. If it's a function, then you want to say, well, is it a 1 to 1 function? Then you do the horizontal line test to see if it crosses it more than once there. It's a very simple test. So this just says use the horizontal line test for these 2 pictures. F of x equals to x squared. This function here would be this graph. And you can see when they draw a horizontal line through it, there are 2 x coordinates that share the exact same y. So it is not 1 to 1. And then when they graph the second one, which is an x cubed, or y equals x cubed looks like this. And they drew a whole bunch of horizontal lines just to check in various areas. None of these cross it more than once. So this is 1 to 1. So just 2 quick examples on the horizontal line test. All right, so that's basically 1 to 1 functions. Short, sweet, to the point. Now we're going to talk about inverses. We're going to determine the inverse of a function defined by a map or a set of ordered pairs. Okay, so suppose that you got a function that's 1 to 1. Then, corresponding to each x in the domain, there is exactly 1 y in the range. Okay? And for each y in the range, there is exactly 1 x in the domain. That is the 1 to 1 definition. The correspondence from range of f back to the domain of f is called the inverse of the function. And they have a symbol for that. It is f, and it looks like it's raised to the -1st power, but f is not a variable here. F is denoting function. So if you have f raised to the -1st, it's saying they want the inverse function of your original 1 to 1 function. And when you're going backwards, basically whatever the domain was, that's now the range. And whatever the range was, that's now the domain. So let me highlight the same colors here. When you're mapping from the x coordinates over to the y coordinates, here's the domain of your function, here's your range of your function. If you reverse it, which they call the inverse, and you go backwards, now what originally was the range is now the domain. And what was originally the domain is now the range. Basically, to get the inverse, you just switch your X and Y coordinates and then graph that list of ordered pairs. And what you get is a mirror image of what you started with. And that's called the inverse. So it says, let's see, to do this example, find the inverse of the following set. So when I'm looking at this and I see that -3, -2, -1, 0, 1, 2, and 3, those are my domains. And here's what they said here. The domain of the function is all of that. The range are all these guys, which I'm highlighting in pink. Okay, and then they said the range of the function is that. All you're going to do is switch them. You're literally going to switch them. So they're going to take the -3, -27, and they switch it. They put the -27 as the X coordinate and the -3 as the Y. And they do that for all of them. Instead of -2, -8, it's -8, -2. Instead of -1, -1, well, that's the same damn point, isn't it? -1, -1. Same thing here, 0, 0. If you switch it, it's still 0, 0. 1, 1, when you switch it, is still 1, 1. 2, 8 switches to 8, 2. 327 switches to 27, 3. So, and now the domain of the inverse function is, and they're just switched. The domain is actually the pink ones from before, and the range, right? This is your new domain. The domain of the inverse function is, these are the pink ones from before, and the range is the blue ones from before. They just switch. I wish I'd draw a picture of that, and they didn't. I guess I could have added that, and I didn't. Oh well. There is a picture coming up. Oh, this goes back to something that we did Monday, but we didn't really, I think, know what we were doing at the time. We were doing composite functions, you know, f of g of x. And if we showed that f of g of x equaled g of f of x, which ultimately they both ended up equaling just x, this will always happen when you're dealing with inverses. So if you do the inverse of f of x, let's do this. If I do the inverse of f of x, that will equal x. And if I take the function of the inverse, that should also equal x. Composite functions. If they are true inverses of each other, you will always get x when you do it. And you can use that as a test to see, like when they ask you to find the inverse and you're like, okay, this is the answer I got. Is this right? Did I do my algebra right? Well, you could always, you know, check them composite wise and see if they both equal x, and then you'll know you did it right. But nobody ever does that, but you could, like they do in this example. It says verify that the inverse of f of x equal to 1 over x minus 1 is this right here. They're saying f negative 1 of x is going to equal 1 over x plus 1. And then it says for what values of x is the composite function equal to x, and for what values of x is blah, blah, blah. Okay, so they calculate, they do f of negative 1 of the function. They're going to put the blue function into, here's the blue function. The original function will be blue. They're going to put all of this, which is the function, into the other function where the x is. So instead of 1 over x plus 1, they've got 1 over, and they used pink. I would have used blue here. 1 over x minus 1. And then they simplified that. Another color. This part right here, if you have 1 divided by 1 over x minus 1, you can write it like this: 1 divided by 1 over x minus 1. And then by fraction laws, when you divide, you change it from dividing to multiplying by the reciprocal. And 1 times an x minus 1 over a 1 is just x minus 1. So instead of that ugly fraction plus 1, we get an x minus 1 plus 1. And then the 1's cancel out, and ta-da, you're left with x. Provided, because it then says, for what values of x would it equal x? Everything but 1, because if you put a 1 right here, 1 minus 1 gives you 0, and 1 over 0 is undefined, so they have to leave that out. And then they do the other one. Now they do the original function and plug the pink function into it. So they're now going to take the pink function, which is 1 over x plus 1, and they're going to plug that into the blue function right here. So instead of 1 over and x minus 1, we've got 1 over, and here it is, 1 over x plus 1, a minus 1. Now this one's a little bit more difficult. No, it's not. The 1's cancel out, now that I look at that. Down in the bottom, this plus 1 and that minus 1, they just cancel out. So you're left with 1 over a 1 over x, which is 1 divided by 1 over x, which by the laws of fractions would be 1 times the reciprocal. And there's just x. But on this one, so here you got just x, provided that x does not equal 0, because right here, if you stick a 0 there, that causes, division by 0 and things implode and you can't do anything there. So they were just trying to show you that they are inverses. I verified it because when I did the composites of each, I got an answer of x, period. Okay, now here comes the pictures. Obtaining the graphs of the inverse function, you're basically just switching your x and your y coordinates. So whatever your original function is, and I'm going to keep with the blue theme here, whatever the original function is, every point has an ordered pair of a and then b. If you look at every point, it will be a mirrored image of it, and it'll have the coordinate of b and then a. So if this is the point, I don't know, 2, 3, then this would be the point 3, 2. And that mirror image happens along this line right here, which is the line y equals x. Before, when we were doing some graphs, things, and I gave you the example of, when you're in elementary school and you had that line of symmetry when you're doing Valentine hearts, and you cut them and the heart opened up and you had a perfect mirror image on either side. But we did that, we were doing it along the x-axis and along the y-axis, and we're actually going to do that, some more of that today. But for inverses, they always fold along the main diagonal of your graph, and the main diagonal is literally the equation of y equals x. Y equals x. So when you're on this line, like this point here is 1, 1, and this point here is 2, 2, and this point here is 3, 3, and 4, 4, that's that line where the x always equals the y. So when you do the inverse, you get a mirror image. For example, this guy. The original graph was the blue one, and the inverse is the pink one. And you can see, and I don't know why they didn't draw this as a dashed line, because technically this line isn't really supposed to be there. It should be dashed because it's a line of symmetry, but you can see it goes right down the middle of it perfectly. If I were to fold it, if I were to fold my paper along that line, the pink part would line up perfectly on top of the blue, or the blue on top of the pink, you know. So that's all that's happening there. And then they have another example, the graph of figure 15a. Okay, so figure 15, here's figure 15, part A, is that of a one-to-one function. They want you to draw the inverse. Well, the only way you can do it is to simply use the ordered pairs. So I would take, this is -2, -1. I would switch it, and its ordered pair would be -1, -2. And I'd plot that point right there. Then you'd go to this point right here, which is -1, 0. Reverse the ordered pair to 0, -1, and that would be plotted right here. And then they only gave me one more point to work with, and that was this point, which is at 2, 1. And I would switch it to 1, 2, and when you plot 1, 2, it would be right there. And so here's the pink graph, and the original graph was the blue one. And you've got this, this is my line right down the middle. It's my axis of symmetry. There you go. If you folded it over, they'd match up. So if they only give you points, you literally just, you know, do that. Okay, and the last objective, find the actual inverse. All right, there are some steps involved in this. This is all algebraic. Step 1 is if they write f of x, just change the f of x to a y, okay? And then you're literally, step 1 is take the x and the letters x and the letter y and switch places. And then once you've done that, here's where the algebra comes into play. You're going to solve it now for y. And of course, once you're done with y, they will have you put back in f -1 of x instead of y. And then of course, step 3, which nobody ever wants to do, you can check your results by, you know, doing 2 composite functions, but you're in my math lab, you know, so if this were a question on a test where you can't check your answer using my math lab, you might want to, you know, do it on scrap paper real quick and say, okay, it verified, they both came out to be x, so I got the right answer. Now, in order to save some time, I went ahead, and this was the slide. Here's the figure over here, this figure right here. This is the graph. And so I shrunk it down and did the work ahead of time. But the blue graph is 2x plus 3. And they found the inverse, which was the pink one of 1/2 times x minus 3. But I went through the steps to show you how they got it. So step 1, where they have f of x, where they have this, f of x equals 2x plus 3, I took out the f of x and I stuck in the y right here, okay? Then what I did is I switched the x and the y's position. So now I have x where the y was and y where the x was. That's step 1. Step 2, get your algebra game face on and start solving this for y. So I took the x equals 2y plus 3. In yellow there, I subtracted 3 from both sides. It canceled out over here. And then I got x minus 3 equals 2y. Then in yellow, I divided both sides by 2. So that would cancel. And then I got x minus 2, or x minus 3 over 2 equals y. But dividing by 2 is the same thing as multiplying the whole thing by 1/2, which is how they wrote it over here. They wrote 1/2 times x minus 3. But x minus 3 over 2 is the same thing. It's the same. And that's how they got the inverse. And then I went ahead and I thought, okay, what the hell? I'll show the verification process in case some of you want to do it. I calculated f of negative 1x. So I put the pink into the blue. I took, this is the pink, right? And I plugged that into the blue right here, which is what I'm showing right here. And then of course the 2's cross canceled. So I'm left with x, or the 2 times the 1/2 right here, that cancels out. And I'm left with x minus 3 plus 3, and then the 3's cancel out, and boom, there's the x. And then on the other side, I did the same thing, except I put the blue into the pink where the x is. So the original function in red was 1/2 x minus 3, and in place of the x, I put 2x plus 3. And then of course the 3's canceled, and then 1/2 times 2x, the 2's cancel, and boom, I'm left with x again. So that verified it. And they both come out to be x. I know that the 2x plus 3 and the 1/2 times an x minus 3 are inverses of each other. And okay, here's just another example. It says find the inverse. So I just left their work here. You'll notice that it started with, here's the y, and on the other side you have the x's. Well, they switched them. They put the y's where the x was and the x where the y was. That's step 1. Interchange them. And now you have to solve it for y. There is more than one y in this problem. So what they did is they said, okay, let's get rid of this fraction by multiplying both sides by y minus 1. That way this canceled, and they were left with the 2y plus 1. And then over here, they just put the x in front of the parentheses. Then they distributed, they took the x and distributed it and got xy minus x. At that point, they realized, hey, we have an x on the left and an x, or sorry, we have a y on the left and a y on the right, and they need to be on the same side. So they did a 2-for-1 special here. It looks like, let me erase that gray stuff. I'm gonna go yellow on you. They went ahead and subtracted 2y from both sides, and in the same breath added x. That way that canceled and that canceled. Now, of course, x minus 2y, I can't subtract, so they left it as x minus 2y. And then over on this side, you can't add 1 and x, so they left that side x plus 1. Now, since you cannot combine xy and minus 2y, if you can't get the x's together, then you have to factor the x, sorry, keep saying x, I'm solving for y. If you can't get the y's together, then you're gonna pull the y out by factoring out the greatest common factor of y, or just the common factor y. So they pulled it out, and then parentheses came into play here, and why they pulled it to the back, I don't know. Most people pull it to the front like this. Pull the front, pull it out in front, and then you're left with x minus 2. But they left it behind. And then they simply divided both sides by x minus 2, and that mess canceled that mess. So they got y by itself right here. There's the y by itself, and it is equal to all of this, which is in terms of x, and that is your inverse. But you do have to make the stipulation that, well, that's the inverse as long as x doesn't equal 2, because if x equals 2, you get a 0 in the denominator, and things implode. And then the next slide, which I'm not going to go through with you, is just them once again verifying it, but most people don't bother with that. So, okay. And then finding the inverse of a domain restricted function. Okay. Sometimes a complete function is not one-to-one, which this one isn't. This function, which is f of x equals x squared, that's a parabola. That parabola looks like this. If I draw a horizontal line through it, that's not 1 to 1. However, if we restrict the domain to just a certain part of the graph, then we can say that that chunk of the graph is 1 to 1. And they did. They said they only wanted the part of the graph where x is greater than or equal to 0. And that, if here is 0 and greater than, we're going this way, we're talking about only the graph that's in quadrants 1 and 4. You're leaving out quadrants 2 and 3. So if you're like, nope, we don't want any of this, it's out, that's gone. And now you can see when you draw a horizontal line through it anywhere, it only crosses at one place. So, you know, if you make a restriction, okay, fine. So they go through all the steps. They switch x and y, and then they solve for y, which involves taking the square root, and then they went through the check, and then here's the picture of it. So you can see that this was my original graph, which I actually highlighted in green before. Whoa, that's too big. This was the original here. Okay, it's still going too big. There you go. And now they've got the inverse, which is the square root, and that graph looks like this. And of course, that is in quadrant 1 going right through, or this line goes through it. That's y equals x, and you can see that it's a mirror image around that line. Okay, so that takes care of all of that, which now brings me to the My Math Lab portion of the show. And My Math Lab number 3 kind of just has you practice doing some simplification with algebra. When I look at this and I see that I have a 2 over x plus 1 all over 4 over x squared minus 1. When you have fractions within fractions, it's called a complex fraction. You need to get rid of the little denominators. I have a big numerator. When I look at this, I see this is, I see this is my numerator, and I see this as my denominator. But then within those two, I have this little denominator and this little denominator. So the green, the light green is my original denominator, but then I have the pink and the, well, that was supposed to be blue. The x and the x squared are what I call my little denominators. So I have to get rid of the little denominators. And I'm in fraction land, so when you're in fraction land, you have to abide by fraction laws. And the one law that you have to remember here is whatever you do to the denominator, you have to do the exact same thing to the numerator. And my goal is to get rid of both of my little denominators. I want to get rid of this x. I want to get rid of this x and also this x squared in one shot. But I'm only allowed to multiply by one thing. So it's got to be something that x and x squared will both cancel into. And that would be an x squared. So I am going to distribute this x squared times the 2 over x, plus I'm also going to distribute the x squared to the 1. And then in the denominator, you have to distribute the x squared to the first term, which is 4 over x squared, minus the x squared also gets distributed to the 1. And then what's going to happen is this x is going to cancel out one of the x's from my x squared and leave me with the other x. And then x times 2 is a 2x. And then over here, it's just x squared times 1, which is x squared. On the bottom, this x squared totally cancels out that x squared. And so all I'm left with is the 4. And then this is just minus x squared times 1. So that's a minus x squared. And I no longer have a complex fraction. I don't have fractions within fractions anymore. It's still a fraction though, and it's still not pretty. And it also says, let's see, the main directions up here told me to simplify. This is not simplified yet because, again, I'm in fraction land. And in fraction land, things are supposed to be in simplest form. Well, since I'm dealing with polynomials, I'm going to have to factor. From my numerator, I'm looking at the 2x and the x squared. I can factor out an x. And when I do that, I'm left with a 2 plus x. The denominator, 4 minus x squared, that is actually a difference of 2 squares. And it factors into conjugates. It's a reverse conjugate. They have the 4 first, so it's 2 and 2, because the square root of 4 is 2. And then you split the x squared up to be x and x, and then 1 is a plus and 1 is a minus. And then at this point, my 2 plus x on the top will cancel my 2 plus x on the bottom, so that all I'm left with is an x in my numerator and a 2 minus x in my denominator. And that's my answer there. Oh, there it is. Okay, 6 and 8 were really quick questions, so I just put them on the same slide. It says, if f is a 1-to-1 function and f of 5 equals 9, then the inverse function, who has an x coordinate of 9, should have a y coordinate of 5. They've got, let's see, they have the 5 as the x coordinate, and if you calculate f of 5, you get 9. Well, when you reverse it, now they're putting the 9 where the x is, which means that this answer right here should be the 5. And that's the one I'm going to pick right there. Just switch them. 8, if the domain of a 1-to-1 function is 1 to infinity, then the range of its inverse is 1 to infinity. Again, these just both go over the whole concept of 1-to-1, where you're just simply switching your x's and your y's. So the domain for the function is the same thing as the range for the inverse. And the range for the function would be the same as the domain for the inverse if they ask you that question. Okay, for the function on the right, determine whether the function is 1-to-1. Very simple. The answer is no, it is not, because of this right here. Boy, my highlighter is on like a 5-second delay. Here we go. You've got 2 inputs going to the same output. So it is not 1-to-1. That's 2-to-1. The next one, for the following, determine if the function is 1-to-1. All you have to do is look at your x coordinates. They are 2, 3, -9, and 6. Those are all different. And then look at the y coordinates. 9, 6, 11, and -8. They are all different. So yes, it's a function. It's 1-to-1. There's no repeat. Okay, number 15 has multiple parts, A, B, and C. They give you two different functions, f of x and g of x, and they say find f of g of x, and then find g of f of x, and then determine whether f and g are inverses of each other. Okay. So I'm going to call f of x the blue function and g of x the red function. Okay, so part A, we are looking for f of g of x. So the red function is going to be put into the blue. Now the blue function is x cubed minus 3. So you're going to take out the x and put the entire red function in place of that. Right? That's what I'm doing. I am taking all of this and I'm going to put it right here. Oh, whoops, forgot my cubed. This was x cubed, so now it's all this junk cubed. And if you cube a cubed root, they just cancel out. So all you're left with is the x plus 3. And then you still have this minus 3 out here. And then guess what happens? The 3's cancel, so you're left with x. So that's what I'm going to put right here in this box. It equals x. And then it says, give any values of x that need to be excluded from f of g of x. Nothing needs to be excluded because we're doing cubed roots. Remember, stuff has to be excluded if you have an x in the denominator, because denominators can't equal 0. And if you have an x under a radical, if the radical is even, because you can't take even roots of negatives, but you can odds. So there's no problem with numbers here. So it's B, no value should be excluded. Now that was part A. Now we're going to part B. And just keep in mind, this was the blue. And this was the pink. And now we're doing G of f of x. So we're going to put the blue function into the pink one. Now the pink one was the cubed root of x plus 3. So this becomes the cubed root of, and we're going to take this x cubed minus 3, and you're going to stick that right here. So instead of x, I'll have x cubed minus 3. And then don't forget the plus 3, because that's still there underneath it. And then those 3's will cancel. So now I'm down to the cubed root of the x cubed. And once again, a cubed root and a cubed cancel each other out. So all I'm left with is the x. And once again, no values need to be excluded because cubing and cube rooting negatives works just fine. And then 32, I could have squozed this in, but are the functions f and g inverses of each other? Yes, because they both came out to be x's. Remember, if they equal x, they both equal x, they're inverses of each other. So, sorry, I guess I could have crammed that on here at the bottom, but I don't know. I write kind of big sometimes, so sorry about that. Extra slide. Which brings me to number 18. Okay, now they specifically tell me that this is 1-to-1, all right, so I don't have to worry about that, but it wants me to find the inverse, and check your answer, find the domain in the range of f and f negative 1. Okay. First things first, let me go to the original function, which is this one here. And instead of f of x, I'm going to write y. Y is equal to 2x over 3x minus 1. So, and then I'm going to switch my x's and my y's. So in place of my y, I'll have an x. And in place of my x's, I'll have y's. So this will be 2y over 3y minus 1. This is step 1. All right. Now, step 2 is solve for y. Okay, well, I have got a fraction, so I'm going to clear it out first. I am going to multiply both sides by a 3y minus 1. So that the 3y minus 1s cancel out on the right. But on the left, if I distribute, I'm going to have a 3xy minus x equals the 2y. Okay, keep in mind, you're trying to solve for y. So first thing was get the y out of the denominator. Second thing, I've got y's on both sides. They need to be on the same side. Well, I don't like that negative x. So I am going to switch to a different color. I am going to subtract the 2y from both sides. But in the same breath, I am going to add x to both sides. That way, the x cancels on the left and the y cancels on the right. So on the left side of the equal sign, I now have 3xy minus 2y equals, and on the right, I'm just left with the x. So now I got all my terms with y's in them on the left. Unfortunately, they are not like terms, so I can't do this subtraction. If I can't get my y's together by combining them, I'm going to have to factor the y out. So I'm going to pull out the y. And when I factor him out, I'll be left with a 3x minus 2. Follow me, I'm running out of room. And then to get y by itself, I have to divide off the stuff in the parentheses. And what you do to one side, you gotta do the other. And so bada bing, bada boom, those cancel, and I'm left with y is equal to x over 3x minus 2. And then, of course, just to make it look all fancy, they change out the y for an f negative 1 of x, because this really is the inverse. So you got to label it correctly. And there's my answer, which I'd put in the box where that blank is. And then it says check your answer, but they don't make you actually go through and check it. But if you did the f of negative 1 of x and f negative 1 of f of x, and they both come out to be x, you know you got the right answer. So, but I'm just going to plug it into my math lab, get a positive affirmation, and move on. So now they're going to ask you, find the domain of f. And to refresh your memory, the function f was f of x equaled 2x over a 3x minus 1. Okay. So if they want to know what the domain of that is, I have a denominator with an x in it. So the 3x minus 1 is not allowed to be 0, which means if I add 1 to both sides and divide by 3, x is not allowed to be 1/3. Boom, there you go. Now, the range. The range, you have to go back to something that we did before, and you have to look at the degrees. This is a 2x to the first in the numerator, and then you got a 3x to the first in the denominator. When the degrees are the same, you have a horizontal asymptote at the ratio of the coefficients of 2/3. And if it's an asymptote, that's horizontal. That means there is no point with a y coordinate of 2/3. So the range is going to be y such that y does not equal 2/3. Little review for you on that. And then that brings us to the next part, the last slide, which then asks you for the domain and the range of the inverse. Now find the domain of f of -1. That's what they want here. Well, just keep in mind, I already know the domain and the range of the original function. So the domain of the original function is now the range of the inverse. And the range of the original function is now the domain. So back here where I had the 2/3 for my range, that's now the domain. So I'm going to click on choice B and say x is not allowed to equal 2/3. And slide one back. Here, the range or the domain was all x's such that x cannot equal 1/3 in the blue. That is now my range for my inverse. So this would be choice C and put the 1/3 in there. It's just that easy. They just switch places. And that is 6.2. You guys got any questions? Those of you that are still awake and I haven't put to sleep. It's getting dark outside. Not even 5 o'clock yet. What the hell? All right.
It's Thanksgiving.
It's Thanksgiving. All right, so I'm switching over to 6.3, and this covers exponential functions. Oh boy, and there's 4 objectives here also. So we'll start with the first one, which is evaluate exponential functions. For some of this, you may need to remember these guys. These are those exponent rules. They've got a to the s times a to the t equals a to the s plus t. This one right here. So an example of that would be if I had x to the 3rd times x to the 5th, it would equal x to the 8th. And then the next one is if you have a power raised to a power, for that one would be an example of if I had x to the 3rd raised to the 4th, that would be x to the 3 times 4 is 12. And then this one just says if you've got parentheses, everybody gets raised to that same power. And I can make it real complicated and say a squared b to the 5th and raise that to the 3rd. That's going to end up being a to the 2 times 3 is 6 and b to the 5 times 3 is 15. Hey, I just noticed they kind of left one out here, but maybe you don't really need it in this section. The next one's pretty self-explanatory. 1 raised to any power equals 1. And then this one down here, a to the 0, also equals 1. And then you got this guy in the middle, which is the negative exponent rule. A to the negative s is the same thing as 1 over a to the positive s, or all of 1 over a to the positive s, because 1 to anything is just 1. The other rule I was thinking about was if you had a to the s divided by a to the t, that's a to the s minus t. So if I had x to the 6th divided by x to the 4th, that would be x to the 6 minus 4 is 2. Those are those laws of exponents. Okay, so anyway, an exponential function is always going to look like this. And you may or may not have a coefficient. They used a big capital C there. There could be a coefficient there. You could have a 2 or a 3 or a 5, or it could be invisible, which means it's a 1. It could also be negative. It just can't be 0, because if C, right here, they say C is not allowed to equal 0. If C was 0, it'd be 0 times a to the x, which would be 0, and that wouldn't be exponential anymore. An exponential function is called an exponential function because your x is in your exponent position. Normally, when we do polynomial stuff, we deal with x raised to some power of a, where a is a number, like x squared, x cubed, x to the 7th, right? Those are polynomial functions. What we're doing is the reverse. We're doing a raised to the x. So now it's like 2 to the x, or 3 to the x, or 7 to the x. They're switching places. So your unknown is actually your exponent, okay? C, which could be a number or it could be an invisible one, they call that the initial value. A lot of times with exponential functions, you work with growth and decay. I do this a lot in calculus. You know, like bunnies and kittens, they grow exponentially. And the COVID-19 is growing exponentially. If you look at those graphs on TV, they go like that. That's an exponential growth. Decay would be the other way around. Decay, decay like dead bodies and stuff, you know, decays like that. It starts out decaying pretty quickly, but then when it gets down to, you know, the end, it takes a long time for those bodies to decay. So, but the other thing is for the growth, it starts off slowly and then shoots up real fast, starts growing exponentially. So anywho, and that's what these graphs I just showed you. Here you go. There's the basic graph of a to the x. They don't have a capital C. It's really an invisible 1 a to the x. These things have some properties. They will always go through 0, 1. All right, no matter what a is, as long as a is greater than 1. All right, as long as it's a whole number. It could be a mixed number. It could be like 7 halves, but that's considered a whole number. So anything that's greater than 1, it'll go through 0, 1, and then it will also have these 2 points. When x is 1, you know, a to the 1 is equal to a. And then this point over here, when a is negative 1, if you have a to the negative 1, it'll be 1 over a to the positive 1. Those points will always be there. Now, how fast it shoots up, like sometimes it shoots like that, sometimes it shoots like this. It just depends on the base, whatever the base is, okay? We're not going to worry too much about that, but that's what the exponential graph looks like. And then the next slide talks about these properties. The domain is the set of all real numbers. It goes from negative infinity to positive infinity because this graph spreads out along the x-axis, then goes through 0, 1 and shoots up. But as it shoots up, it keeps going in this direction and it keeps going in this direction that way. So it spans out across the entire x-axis. This thing spans out across the entire x-axis. So the domain is negative infinity to positive infinity. There are no x-intercepts, and the y-intercept is 1. There's no x-intercepts because the x-axis is an asymptote. It is an asymptote. Remember, y is, since this is usually applied to exponential growth and decay, y can't be negative. It's all or nothing, but it can't be negative. And then that's what I said in number 3. The function f of x equals a to the x, a is greater than 1, is an increasing function and is 1 to 1. It's increasing when you look at the graph. It's going uphill, so that's increasing. And it's smooth and continuous, and like on the previous slide, it contains those 3 points. So now that is if your a is greater than 1, if a is greater than 1. But what if the base is between 0 and 1, which means it's a fraction? Well, basically what happens is this thing flips around the y-axis like a weather vane, and we've done flipping like that before. They're saying that a is between 0 and 1. So let's say we'll go with like 1/3. All right, let's say a is equal to 1/3. That's between 0 and 1. So what we're looking at here is a 1/3 to the x power. But I could also write this as 1/3 to the x power. And 1/3 to the x is the same as 3 to the negative x. And if we go back to graphs that we did before, when the x had the negative on it, when the function part had the negative on it, it flipped, it spun around the y-axis. If the negative was in front of the function, then it flipped around the x-axis. This goes back a ways. Can't remember how far along back we did that stuff, but I'm sure you remember me talking about weather vanes. So it can either be a is between 0 and 1, or it's either, didn't need to do that, sorry. It's either this, or you've got a negative exponent. Because some of the matching graphs we have to do, they won't have bases that are fractions. They'll throw in the negative exponent. So I had to kind of explain it here. That's what happens on the negative exponent. And then here's all the same properties as before. So you can read that at your leisure. And then here's the 2 pictures side by side. And you'll notice on this one here, they wrote it 2 to the negative x is the same thing as 1/2 to the positive x. Everything I saw in my math lab, though, so far had negative x instead of a fraction. So, and you'll see that when we get to the examples. Next, we're going to do transformations again with these guys. We've done transformations before, so real quickly. If they want you to, what was the graph? They wanted 2 to the negative x minus 3. Y equal 2 to the negative x minus 3. So they tell you to start with the basic graph of y equals 2 to the x. And that is what my math lab will do also. When you click on the graph and you click the exponential tool in the toolbox, it'll start with y is equal to 2 to the x or 3 to the x or whatever base it is. And then you'll have to tell it how to shift. So they started with that, and then they said, okay, so let's look at looks like they went with the negative x part. So they now shifted it 2 to the negative x. That's gonna spin it around this point right here. It's going to spin it. So originally it was going like this, and now when you spin it, it's going to be going down like that, but it still goes around this same point here. And then they want to do the -3, since it's the entire 2 to the negative x, and then they do a -3 after that. Remember, if you add or subtract, it goes up or down. And so it's down 3. So they went from here and went down 1, 2, 3, brought me to this point here, and there's the graph now. It was at 0, 1, and it went down to 0, -2. Oh, I guess it didn't really start there. It started here, didn't it? Let me use a color instead. It was right here, and then it went down 1, 2, 3 to there. And that's the final graph right there. And we've done this before with other graphs, parabolas and stuff. Okay, now, there is one special exponential function that involves the number e, and this was figured out by some dude named, I think I spelled that wrong. Yeah, I did. Euler. I always say Euler because it sounds like Bueller, you know, from Ferris Bueller. But you just need to know that E is actually a very specific number. It is defined from the expression of 1 plus 1 over n raised to the n. And then this guy did a whole bunch of work with it and said, okay, what happens when n gets bigger and bigger and bigger? When n gets closer and closer and closer to infinity? And so he kept a table and he kept doing the math. And you can see it started out as 2, and then started out as 2, then 2.25, then 2.4, 2.5, 2.7, 2.7, 2.7. He started getting the same 2.7, but then all these other numbers, it kept getting closer and closer and closer to a very specific number. And so he said, hey, I'm going to give that number a letter, just like pi. You know, everybody knows that pi is 3.14, blah, 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 blah. Well, E is 2.718, blah, 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 blah. He is another irrational number. So that's E, and that's all you really need to know about that. But the properties of his graph are the same. He's going to go through 0, 1. This point will be 1e. This point will be -1, comma, 1 over e, just like any other base a. It's the same concept. And then here's another example where they had you graph -e raised to the x minus 3. So they start you out with the e to the x graph. If you remember this negative right here, since it's negative in front of the entire function, that's going to reflect it around the x-axis. So now it's going like this, upside down, flipped down. And then you've got this x raised to the x minus 3, because of that 3 up in the exponent, that's going to shift left or right. And it's always the opposite. So this is going to go 3 to the right. So it was this point here, it's going to go 1, 2, 3 to the right and land right here. And the graph's going to look like that, which is what this is right here. Transformations. Fun times. And the last concept, I think, was solving exponential equations. And in order to solve equations, you need one basic rule, and it is this. If a to the u equals a to the v, then u equals v. I would always say if x to the a equals x to the b, then the a equals the b. I would always tell people, if your bases are the same, then that means your exponents are the same. And because the bases are the same, you get to just drop the base. And then I always try to ask a student to drop a base for me in class, you know, something like that. Not everybody tries to do that for me, you know, drop your base, but anyway, okay. So here's some examples. The only way to use that previous rule is to make the bases the same. Now, if you can't make the bases the same, then you go to logarithms. Now, we haven't hit logarithms yet, so every problem that you deal with in my math lab in this section, you will be able to make the bases the same. And when I'm looking at the left side, I have a base 3 here. So my question is 81 base 3? Yes, it is. 81 is 3 raised to the 4th power. So I literally changed the 81 into its base 3 form, because 3 to the 4th, 3 times 3 is 9, times 3 is 27, times 3 is 81. And now I have 3 to the x plus 1 equals 3 to the 4th. I have a 3 to the this equals a 3 to the that. So this equals that. I'm literally just going to drop the bases and say that the exponent of x plus 1 will equal the exponent of 4. And then I would simply subtract 1 on both sides and get x is equal to 3. And the question is that correct? If you stick 3 right here, 3 plus 1 is 4, and 3 to the 4th, yep, that equals 81. Now, on that problem, I only had to mess with one side of the equation. But on the next one, which is part A again, okay, that looks like a major typo. This should be part B, I think. Hello. This time I have a 4 and an 8. So I'm actually going to have to change both of them to the same base, because 8 is not a base 4 number. 4 to the 1st is 4. 4 to the 2nd is 16. Flew right on past the 8. 4 and 8 are base 2 numbers. I'm going to change this 4 here to a 2 squared. And I'm going to change this 8 to a 2 cubed. And then I have power to a power on both of those. So I'm going to have to multiply. This is going to become 2 raised to the, if you take 2 times a 2x minus 1, you have to distribute here. So this is going to become a 4x minus 2 equals, and then on the other side, it's going to be a 2 raised to the, I've got a 3 times an x plus 3, power to a power, you multiply, but I have to use the distributive property to multiply them, and I get 3x plus 9. And now I have a 2 to the this equals a 2 to the that, which means my this equals my that. I'm literally just going to drop the 2's, and I am going to say that the 4x minus 2 equals the 3x plus 9. And now I have to solve that. So follow me up here, kind of ran out of room. And I'm just going to put it all in black. 4x minus 2 equals 3x plus 9. So to solve this, I would subtract 3x from both sides. Cancels out there, but in the same breath, I'm going to add 2 to both sides. So it cancels out there. 4x minus 3x is x, and 9 plus 2 is 11. And I think that's what they showed here. Yep, x equals 3 and x equals 11. So They showed the same steps that I did. And solving an exponential equation, solve e to the negative x squared equals e to the x squared times 1 over 3. Oh boy, I'll just show you their work. They started with the right side. This was the right side. And they put this over 1. And then they changed. No, they didn't. They did power to a power. They took e to the x and squared it. That gave them e to the 2x. And then they took the 1 over e cubed and changed it to e to the negative 3. And then because they had an e to the 2x times an e to the 3, you're supposed to add your exponents together. So 2x plus negative 3 would be e to the 2x minus 3. And that's what they put on the right side. This was the left side from the original problem. So they just took this right here and simplified it. And they simplified it to be this right here. And now you have an e to the this equals an e to the that. If you look at it, both sides have a base e. I have an e to the negative x squared. So there's the negative x squared equals an e to the 2x minus 3, 2x minus 3. They just dropped the e's out. Now, unfortunately, this one is a quadratic because you have an x squared. So they set it equal to 0, and it looks like they actually moved everything to the right side to make the x squared positive, and then they factored, and then they got the 2 answers. So they unfoiled that because you've got an x squared here, so that's x times x. And then at the other end, you've got the minus 3. So they did a plus 3 and a negative 1, which adds up to the positive 2. Got it factored, and the 2 answers are negative 3 and 1. Okay, well, I gave it the old college try, but here's my math lab number 2. Here's a picture of your calculator just to show you. Number 2 wants you to approximate this using a calculator and rounding your answers. The first thing I would do is 1/4. I'm going to change my 1/4 right here to 0.25, just so that I'm dealing with all exponents. And then on your calculator, you need your exponent button, which for you guys, the exponent button is this one right here. It's the y to the x. So if I were using this calculator, I would type in 8.2. And then you can either use the parentheses if you want or not. That's up to you. So I'd type in 8.2, and then I'd probably just hit the multiplication sign, and then I'd type in 0.25, and then I'm going to hit that y to the x button, and then I'll hit 2.6, and then I'll hit my equal sign. Your calculators are programmed to do order of operations. So if you type it in as exactly as you see it, it will do it correctly. It should. So anyway, it's 5:16 and I'm out of time. So I'm going to finish this up and also do 6.4 next Monday. And that should get me back on track because 6.3 was supposed to be today. So I got started on it. Y'all have a very nice Thanksgiving, and don't eat too much, don't drink too much, don't argue with the family too much. And hey, I got to do my math homework is always a great excuse of getting out of doing dishes or just, you know, having to dismiss yourself from the table, you know, if you need to.
So there's not going to be any modifications to the math schedule. The 2 that are on there are going to be due when the due date says.
No, I'll change that. Well, 6.2 will be done, should be done by Sunday. But since I didn't finish 6.3, I'll change that.
All right, thank you.
You're welcome. Bye, y'all.